Imagine a drone flying through a complex, cluttered environment, or a robot arm collaborating with human workers. In these scenarios, the robot needs to perceive its surroundings in order to avoid collisions with obstacles or their human co-workers. One way to enable such perception is to use single-pixel proximity sensors. These sensors typically return a single or sparse set of true or false values, and are not suitable for robot navigation through scenes with complex geometry, for example, a narrow gap. Another potential approach is to use depth sensors, such as structured light or time-of-flight cameras. However, these sensors usually require high computational or power budget and a low resolution, which is not suitable for low-power devices, such as a micro drone. In this paper, we propose weak 3D cameras, which recover only weak representations of scene geometry that are less informative than full 3D maps, but requires less computing power, shorter acquisition time, and lower hardware complexity. To this end, we propose a novel motion-centric scene representation called Inertial Safety Map, or ISM, which is the product of scene depth and time to contact between the camera and the scene. It is called Inertial Safety Map because it measures the level of safety if the camera keeps its current motion. We show that with a structured light system, ISM can be computed with low computational budget, which enables fast, conservative collision avoidance. The inertial safety map is a motion-centric representation. For the same scene, different camera motions result in different inertial safety maps. Please refer to the paper for a detailed discussion. Since inertial safety maps are less computationally intensive, it is affordable to compute them at very high resolution in real time. This enables detecting thin obstacles in real time for robust robot navigation and manipulation, even in cluttered scenes. In this example, we show how the proposed method can be used to recover thin fences. Commercial depth cameras such as Connect V1 and V2 cameras cannot recover the correct depth of the fences due to their limited spatial resolution. Our method is able to recover the high-resolution inertial safety maps with the thin structures. Here is another example with a few metal rings made of thin wires in front of a box. Our system can recover both the rings and the box, while the Connect cameras completely miss the thin rings. Next, we show a few example scenarios that demonstrate how the proposed techniques can be used in robot navigation scenarios. The inertial safety map is used as a conservative measure for collision detection. When a danger is detected, the robot slows down and initiates a full depth recovery algorithm in a separate thread. When the depth estimation is finished, it is used for planning a trajectory to navigate through the obstacles. This is a challenging example with intricate obstacles. The thin threads are detected from the recovered ISMs, and the drone rotates to prevent collision. We implemented our method on a proof-of-concept hardware prototype consisting of a projector and a camera, placed on a moving cart. Due to the simplicity of the hardware, it can be readily miniaturized in the future. We use this hardware prototype to simulate a robot navigation scenario by manually moving the cart. The robot detects the danger of the pillar and decides to turn left. In addition to camera motion, inertial safety maps can also be used to detect collisions due to object motion. Avoiding collisions with dynamic objects is important for co-robots, where robots and human workers work in the same environment. In this video, the hand is detected as a danger as it approaches the camera. Here we show a more challenging example where the approaching object is a thin, dark cable with a width of only a few millimeters. It is still detected as a danger in the recovered inertial safety map. In summary, we proposed the inertial safety map, which is a motion-centric scene representation for collision detection. We show that with a structured light system, the inertial safety maps can be computed efficiently. As a result, high-resolution inertial safety maps can be computed in real time. This allows fast detection of extremely thin obstacles, which is important for applications such as drone navigation and coal robots.